All right, so the last unit we're reviewing is modern physics, right, for AP Physics 2. And so there's a lot of various topics. It's not very quantitative or analytical. So it's primarily very conceptual because a lot of these topics are pretty advanced. So let's talk about atomic structure and quantum state. So atoms have a nucleus made of protons and neutrons. They have orbiting electrons. Number of protons indicates the property of the material. That's where you use a periodic table of elements. Atoms can have different number of neutrons, call them isotopes. Mass number is the number of protons plus the number of neutrons. And the strong nuclear force is the fundamental force that allows neutrons and protons to be bound together, stronger than the electrostatic force. So the Bohr model of the atom, electrons orbit the nucleus like planets orbit a star. So it's like thinking about like the nucleus, the protons and the neutrons, and the electrons orbiting it. That's a classical model. It's not how the electrons really work, but it is an interesting model. You're basically using just the electrostatic force of attraction and centripetal acceleration as a model. But the standing wave model of electrons is the more modern version, right? Electrons orbit in different energy states. They are discrete states. They are quanta, right? They can only jump between specific states. So it's like if you were to think of it as like orbiting, they could only orbit at certain locations, rather than being like a continuous spectrum of various orbits, right? So this is what we call a quantum states. To move into a higher energy state, in order for an electron to gain energy, it has to absorb a photon. And to go into a lower energy state, the electron must release energy by releasing a photon. So photons contain energy. Those are light particles. The binding energy for an electron to be bound to an atom is the amount of energy for the electron to escape. So if you give the electron, you hit it with a photon with the greater than the binding amount of energy, then it will escape, right? Energy classically, right? We normally measure energy in joules, but we will sometimes use electron volts to measure energy for very small energy levels. And there's a conversion. I'm pretty sure the equation sheets have conversions for there if you want. Mass energy equivalence is that mass itself contains energy. So E equals mc squared, where m is the mass of an object, E is the energy, and c is the speed of light. So c squared is a very big number. In a reaction, you can compute how much energy is released or stored by looking at what we call the mass defect. That's the mass that's lost in it. So, for example, if you have a nuclear fusion, you take two hydrogen atoms, they form a helium atom, but you lose a little bit of mass. That mass that's lost, called the mass defect, multiplied by c squared is how much energy is released in the reaction. So light is made up of particles, photons. We still think of them having wave properties. Photons have an energy equal to hf, which h is, so they don't have any mass, but they still have energy. Hf, where f is the frequency of the photon, right? They have a wavelength. The Broglie's wavelength for that light can be found by taking Planck's constant h and divided by the momentum. And the momentum of the photon, you can rearrange this, is given by this. Now, careful, momentum of photons is not mv, because if you do mv, the momentum would be zero. So we use this to talk about the energy, the momentum of the photon, which is non-zero. So it has a non-zero amount of photon despite the mass being zero. So we use this for the equation for the photon when you're talking about the momentum of a photon. Photoelectric effect. This is the thing that basically says that if you shine, this is what showed that light was made up of photons, right? Because what ended up happening is the photons themselves needed to have a certain amount of energy. So you shine light on a metal at a certain energy. If you get the frequency high enough of the photons, it will eject electrons. That's because the photons hit the binding energy amount. And hit the electrons, and then they can escape. So it's not about how much light you shine. It's specifically about the frequency of the light or the amount of energy stored in the photon, right? The kinetic energy of the escaping electron is given by the energy in the photon minus the work function. The work function is almost, think of it like the binding energy. It's like how much energy it's required to cause the electron to escape, and any excess energy then goes into kinetic energy of the electron, right? So because this is the key thing, this is why it was such an important, this is why it was considered groundbreaking, is because it's only the photon energy is affected by frequency. Shining brighter light, which is more photons at the same frequency, is, even though you're sending more energy overall, it's not interacting with the electrons to cause it to escape, right? It will not change the amount of energy given to the electrons. It has to be the energy of the photon, of the individual photons themselves, that affect it. Compton scattering is when photons interact with a free electron, so energy and momentum is transferred to the electron. So the photon loses some energy, loses some momentum, and frequency and wavelength, they all change. So what ends up happening is because you give some kinetic energy to the electron, so it hits it, the electron scatters off, the electron gains kinetic energy, so the photon must lose some energy, and that means lower frequency or higher wavelength. The momentum is going to change because of the scattering, because it's still overall the momentum is conserved, because remember, photons have some momentum. And then we talked about the frequency and the wavelength. The formula you're given, this is deriving it just based on using conservation of energy and conservation of momentum, but the change in the wavelength is given by h divided by mass of the electron times the speed of light times 1 minus cosine theta, where theta is the scattering angle here. Okay, so what you can do is figure out what the change in the photon is, and that's going to give you the wavelength. That's going to give you the change in the energy. So when it scatters, the wavelength is going to get longer because it loses some energy in there, right? Because the energy in the photon is proportional to its frequency. Blackbody radiation is that matter when it's warm will release some thermal energy into electromagnetic energy, right? So it like lights up. So the warmer the temperature, the higher the energy the photons are emitted, right? Because warmer temperature means more energy. So the warmer the temperature, the higher the energy of the photons. What that means, that's higher frequency or smaller wavelengths. Right, and so that's why the wavelength is inversely proportional to the temperature. The greater the temperature means the greater the energy of the photon, which means the smaller the wavelength. Smaller wavelengths is higher frequency, right? Because wavelength times frequency is speed of light, right? So as the frequency goes up and the energy of the photon goes up, then the wavelength goes down. The rate at which energy emitted is given by this. So if you're talking about like, it's the surface area times a constant times temperature. The key thing is just to understand the fourth power temperature on that dependency there. Last part is nuclear decay, right? And so there's different nuclear decays, and they're governed by the strong nuclear force again, or that's the interaction between the protons and the neutrons. You have three primary decay mechanisms. One's an alpha decay, where an atom meets a helium nucleus, which is 2 protons and 2 neutrons. So that is going to change significantly the mass of the atom. A beta decay, you have a beta positive where a proton's converted to a neutron and a positron or a positively charged electron is emitted. Or you have a beta negative decay, which is the neutron is converted to a proton, but in order to keep charge conserved, an electron is committed, right? So this is a positive and a negative, so the net change is 0. And same thing here, because you go from positive to a neutron, you're going to lose a charge, so you have to have a positive charge to offset it in order to say that because you can't create charges, right? Charges cannot be created or destroyed by conservation of charge. Sometimes in a beta decay, a neutrino has no charge and very negligible mass is emitted to conserve momentum for the only purposes of doing momentum conservation there. You don't need to understand much more than that. Gamma decay that's where electrons are just are changing between states, and that releases a photon. So these two change the nucleus of an atom, right, by either losing protons and neutrons or converting protons into neutrons. This one just releases energy, and that's it. During all of these processes, momentum, energy, mass, and total charge has to be conserved during these decay processes. So all 4 of those things have to be conserved during that process. Decay is a random process. The number of nuclei remaining in the sample is given by this equation, where this lambda is the decay constant and n0 is the initial amount of material. So we've done half-lives. This is where we're talking about half-lives, where it's like the amount of time until you have half of the material remaining. Is T1/2. That's our half-life factor there. And so let's go look at some multiple choice and free response questions here. So at time t equals 0, sample of radioactive material with decay constant lambda has n0 nuclei. At time t equals t1, there are n1 nuclei remaining. At a later time t2, there are n2 nuclei remaining. Which of the following calculates n2 to n1? So n is going to be n0 e to the negative lambda t. Then we know n1 is just going to be n0 e to the negative lambda t1. And we know n2 is just going to be n0 e to the negative lambda t2. So we want to know like how to solve for n2 in terms of n1. What you can do is just solve for n0 here. So you get n1 over e to the negative lambda t1 is equal to n0, and plug that into here. So you get n2 is going to be n1 over e to the negative lambda t1, e to the negative lambda t2. Because these are both the same base e, you're just going to subtract their exponent, so it's going to be negative lambda t2 minus t1 if you do that. And so that's why you're going to get something like that. And that is going to be in your, because if you pull it out, you subtract T2 minus T1. So it's going to be, let's see, it's not C. Oh, yeah, it's A here. There's no N0 here, right? Because we replaced the N0 with this quantity here. Okay, blackbody temperature T0 emits a spectrum of light with peak wavelength lambda 0. The rate at which energy emitted is P0. The temperature of the blackbody is unchanged, so the new peak wavelength is lambda 0 over 2, which, if found correctly, indicates the rate at which energy is emitted. So remember, the power is going to be area times the surface area times that T to the fourth. That we got that T to the fourth dependency. And you also have to remember that the maximum wavelength is like some constant over temperature. So what happens is if you are going to change the maximum wavelength by 1/2, then that means the temperature has to be multiplied by 2 on the denominator, right? In order for the two equations to be balanced. If we multiply this by 2, then this side's going to be multiplied by 2 to the fourth times 16. So we're going to get D there. Okay, so we have an electron in an atom is initially bound state with negative E1. It absorbs a photon, transitions to excited state negative E2. So let's think about it like we have E1, and it's gonna absorb a photon, so it's gonna jump up to E2, right? So it absorbs a photon, and after a brief time, the electron drops to a lower energy state with negative E3. And so we'll put a negative sign here if you want, and then it's going to drop down to E3. Could be above or below, but we're going to drop to E3. It observed that the photon emitted during the second transition has a higher frequency than the photon absorbed during the first transition. Is the magnitude of the energy change in the second transition greater than, less than, or equal to the magnitude of the energy change in the first transition? Well, because there's a higher frequency, right, it's going to have more energy. Right, so this emitted photon has more energy, so it's going to drop down to here like this and become negative E3 like this. So this is kind of the picture, because you have a bigger energy difference, right, which means more energy of the photon emitted here. And so then because you emitted a larger photon or more energy photon, it's going to have higher frequency. So that's consistent. So it's going to be greater than. And we want to do that qualitatively, and we just want to say it just like we did. We said a higher frequency photon means that it was a larger amount of energy, more energy, larger energy photon. And that requires a greater energy change, G state change, right? Because the energy state change is what impacts the energy of the photon. Derive an expression for the frequency of the absorbed and emitted photons. Express your answer in terms of E1, E2, and E3 and fundamental constants. Okay, so we know the energy of the photon is going to be lambda times the frequency. Sorry, it's going to be Planck's constant times the frequency. Now, for the first photon, the emitted, you always do, if you want the energy of the photon, it's going to be larger minus smaller. So it's going to be, let's see, negative E2 minus negative E1. So E1's like a bigger number in magnitude, but like we're thinking of it because these are negative, that's the energy of the photon. This is the emitted photon. This is H of the frequency emitted. No, sorry, this is the absorbed one. This is the first state. Because we're going this state, we're absorbing a photon, so we're going up absorbed. So F absorbed is going to be negative E2 plus E1 over H. Okay, and then we do a similar thing for the one that is emitted, right? So it's going to be negative E2 minus negative E3 is going to be H times the F emitted. So the F emitted is going to be negative E2 plus E3 over H, like that. Okay. Rank the values of E1, E2, and E3. And we look at this diagram here. So it might help just because the negative sign is a little bit confusing in this question. Think of this as like negative 10, negative 8, and negative 6. So then you think of it as like E2 is 6, E1 is 8, and E3 is 10. So then if you want to just rank those numbers, you would just say E3, then E1, then E2, right? So it'd be E3 is greater than E1, greater than E2, like that. Okay. So sometimes if you're symbolically, you can't rank them, just putting numbers in here can be helpful like this, right? Okay, let's look at this one. Experiment, a monochromatic light of frequency F is incident on a metal surface of work function phi. Electrons are emitted from the surface and enter a region of a uniform electric field directly opposite of their initial velocity. The electrons travel a distance d through the field before coming to rest. Is the stopping distance d of the electrons greater when the frequency of the incident light is increased, assuming all conditions stay the same? Okay, so what's happening is you are sending photons, right? They're hitting a metal, and then we're ejecting an electron this way, and we're putting an electric field. The electric field's this way because these are negative charges, and it's gonna apply a force on the electron opposite direction of the electric field, and then eventually they're gonna come to a stop here, right? So he starts off with some kinetic energy, and will eventually come to a stop, or starts with some velocity. Now, the higher the frequency, when you have a greater frequency, what happens is you're going to have more energy in the photon, and so then you're going to have more kinetic energy left over. More kinetic energy means it goes faster. If it goes faster and you're pushing it with the same force, then it's going to come to stop at a greater distance. So it's greater, and that's the reason you want to say. So you want to say greater frequency of the photons means more energy in the photon. So the resulting kinetic energy of the electron increases, which means it travels further. Further? I don't remember. Farther in the same E field. Okay. Derive an expression for the stopping distance. So we want to think about how much kinetic energy we have, is we're going to have whatever the energy of the photon is minus the work function. So that's going to be HF minus the work function, right? So we're going to start with kinetic energy. We're going to end with zero kinetic energy. So we have to just think about, like, in terms of the distance, I would think of work as change in energy, right? So we have the kinetic energy. The change in kinetic energy is going to be the work done by the electric field, right? So we're going to end with zero kinetic energy. We're going to start with initial kinetic energy of HF minus phi, and we're doing negative work on it because it's going to travel a distance d, and we're applying a force in the opposite direction, and that force is the electric force, which is Q times the electric field, and then times the distance to get the work. So the negative signs can cancel. This Q, we usually use the letter E to represent the charge of an electron, because that's what it is. So then the distance is going to be, you just divide by EE over here. It's going to be HF minus phi divided by E times capital E. You could probably use Q for the charge if you wanted to, but E is most commonly for charge of an electron. And that would be the stopping distance, right? That's our work energy process. So does that agree, right? So if we increase F here, does that increase the stopping distance? And say yes, because increasing F will increase the numerator HF minus phi, and that implies D is greater. So that's what we said. We said D would be greater when the F increases, right? That's what we said in part A. Okay, let's look at another one here. So we have a sample of unstable nucleus X undergoes a nuclear decay, producing a new nucleus Y. The nuclear reaction is observed to be this, where beta minus represents an emitted electron, and V minus is an emitted antineutrino. Okay, I think that's supposed to be like a bar over it. At time t equals 0, it's not a negative sign, yeah, because antineutrinos are neutral charge, right? Time t equals 0, there are N0 nuclear present. Half-life is measured T1/2. Based on the observed reaction, identify the type of radioactive decay occurring. Okay, so this is just basically definition. We're emitting a beta particle, a negatively charged beta particle. So this is a beta minus decay, because it's based on the charge of the beta minus decay. And we are emitting an electron, right? And an antineutrino there. Okay, suppose NX is the because you're emitting a negatively charged beta particle, a negatively charged electron. Okay, suppose NX is the number of neutrons in the nucleus, PX is the number of protons in the nucleus. How many protons and neutrons does it contain? So we got to think about the change. Now, the total, the number of neutrons, Ny, plus the number of protons of Py has to still equal, like we're still, the total number of protons and neutrons are going to remain the same. Okay? Like this part we know we have to know is to be the same. However, because we have a negative charge here, we're going to have one more proton over here in order to keep the charge like balanced over here. So let's say this net charge was 0. We're going to need a positive charge to cancel out that negative charge. So what that means is a neutron had to get converted into a proton. Okay, so that means a neutron has to get converted into a proton in this reaction. So that means the number of protons in Y has to be 1 more than the protons in X, and the number of neutrons in Y is, you take the number of neutrons in X and subtract 1, right? This shouldn't have said that. It's just sort of a template kind of thing, because hopefully you guys see how that's happening, because we have to have a extra positive charge over here in order to balance out that there was no charges that were just created. Okay, derive an expression for the number of undecayed nuclei remaining as a function of T, N0, T, 1/2. So we have the half-life is here. So remember our equation is N is equal to N0 e to the negative lambda T, right? And so what we know is that with T 1/2, we know that we have 1/2 N0 is equal to N0 e to the negative lambda times T 1/2. You can derive an expression for what that lambda is going to be, because that's what I can't use it as lambda here. So the N0 cancels. You have that. You take the ln of both sides. Ln will get rid of e, so you get ln of 1/2. The ln and e cancel, so you get negative lambda T 1/2. So your lambda is going to be negative ln of 1/2 over T to the 1/2, right? So then you can write this as N equals N0. E to the negative and negative would technically make it positive, ln of 1/2. Ln of 1/2, though, is a negative number, though. So T 1/2. So this would be how you could do it. Or you could have read it as N0 e to the negative ln of 2 over T to the 1/2, if you guys know that one. That's because you can make this, log rules is 1/2 is 2 to the negative 1. You can bring the negative in front and make it just negative that. Or if you didn't even want to do the exponential form, this is from pre-calculus, you could just say like, well, it's N0, it's times T, it's times 1/2, and you do that every half-life. So when T is T to the 1/2, you're exactly multiplying by this, but all of these would be the same. Doesn't really matter. Any of those would be acceptable in the ways you could do it. I think it's more inclined to like look like one of these two just based on the formulas I gave you, but honestly, I would prefer to do this. I think it's more natural for half-life to go with that equation. Okay, suppose after T1, only 33% of this original sample remains. Derive an expression for T1 in terms of T 1/2. So for example, here we're just going to go here and say like, well, we're going to have 1/3. Actually, I should have just made this 1/3. So 1/3 N0 is how much we have left, is equal to N0 e to the ln of 1/2. Just use whichever equations you want. T to the 1/2. Oh, sorry, there should have been a T here. Forget the T. T 1/2, and then this is T1 is the time, right? So I plug in T1, T to the 1/2, and then we just want to, the N0s are going to cancel. We just want to solve for T1. So we're going to take the ln of both sides. So we get ln of 1/3 is equal to ln will cancel with that e. You get ln of 1/2 over T to the 1/2 T1. And then you're just going to say, well, multiply by T to the 1/2 and divide that. So you're going to have ln of 1/3 divided by ln of 1/2 times T to the 1/2 would give you that. You could put in your calculator if you want for that thing. You could make this ln of 3 over ln of 2 because technically it would cancel. Either of those are fine, but that is acceptable. Whichever equation you use there, that's what I would use. Okay. let's do one more FRQ where we do some Compton scattering, just to give you one example of what that looks like. So in Compton scattering experiment, a beam of photons with initial wavelength lambda strikes a stationary electron. Some photons are scattered at angle theta 1, others are scattered at angle theta 2 relative to the original photon, and theta 1 is small, so theta 2 is greater than theta 1, and they're both less than 90 degrees. Is the final energy of the photon scattered by theta 2 greater than, less than, or equal to the final energy of the photon scattered by theta 1? Justify your answer qualitatively without referencing equations here. So now when we want to do this qualitatively without just looking at the Compton equation, we have to think about the principles that are applied. So we have a photon, right, with a wavelength, and it's hitting an electron, and it scatters at an angle, right? So there's an electron at rest here, and then the scattering angle is going to be like that. Right? So it's going to scatter, and then the electron's going to move off. Now, the electron scatters at an angle theta, and this angle is some other angle. We'll just use like phi as it. So we're scattering by this angle. So in our equation for Compton scattering, when we're doing this, which is the, gosh, let me look up the equation that we had up here. I know we did a lot of, so much stuff. H over, right, this equation is what I'm talking about. Mass of the electron, speed of the light over there, like that. Okay. That's what theta refers to, this angle. Now, let's talk about what happens if the angle is greater. So we have a greater angle now. It's less than 90 degrees, so it's going to be greater in this case, right? So two things are conserved. The momentum has to be conserved. So he's going to have... if you think about like this angle here, theta, he's going to have less x momentum and more y momentum, right? So from a conservation of momentum point of view, this thing, whatever the momentum of this guy is, it has to compensate for, it has to compensate in the x and the y direction there. I think at this one, it would be sufficient to just argue and just say like, okay, so the greater the angle change, right, the cosine of theta, that x component is going to be smaller. Cosine of theta is going to get smaller. That's going to go down, right? So this whole overall quantity will increase. So that will increase, which means our change is going to be, we're going to have a greater change in the wavelength. And remember, we're going to lose some energy. So if we change the wavelength by more, we're going to have, and we're losing, right? Because overall we are, so let me think about this. Let me double check. We are, giving some kinetic energy, so we're going to lose some here. So this change in this wavelength means the bigger the change in the wavelength, right, means we're going to lose more energy. So we're going to end up with the final energy of the photon is going to be less than. And so your reference there, I know we're not going to reference equations here, but what we're going to talk about is a larger scattering angle means a larger change, and that means a reduction in the, sorry, larger, not reduction, larger increase in the wavelength of the scattered photon Okay, so we have a larger change and larger, which meaning the photon lost more energy. Okay, so derive an expression for the final energy of the scattered photon in terms of the initial wavelength scattering angle fundamental constants. So here we're going to say, oh, the change in the wavelength, right? This is our first equation because you're given this equation, so you're allowed to do this. ME times C 1 minus cosine theta. Okay, and then that's the change in the wavelength. So the initial energy is going to be, you know, hc over the initial wavelength, and then the final energy, which is going to be E, it's going to be hc over the final wavelength. And this delta theta is how much longer it's getting, right? So if we want to solve for theta f here. So the initial wavelength was just theta, so we're going to move it over. So theta f, the final wavelength, is going to be the initial wavelength plus h over mec times 1 minus cosine theta. And then the energy of the photon is just going to be hc divided by the final wavelength, which is going to be lambda plus the change in the wavelength, right? mec 1 minus cosine theta. Okay, and so we're going to have that. And so does your derived expression agree with your qualitative prediction? So let's talk about what's going to happen here, right? So as we increase theta, so as if when theta 2 is greater than theta 1, that implies cosine of theta 2. So when you increase cosine, when you increase the angle cosine in the first quadrant, the cosine decreases. And that implies 1 minus cosine of theta 2 is going to then be bigger, because this number is going to be smaller. It's going to be greater than 1 minus cosine theta 1. So this quantity is smaller. So that means the denominator is smaller. And the denominator is smaller than the energy. And so the denominator is smaller, which results in... actually, let me double check if that was consistent. Let me work out the reasoning again. So I said our denominator is going to be larger, right? Because you're going to increase this quantity. So the denominator is larger, which implies that E will be smaller. So that's kind of the reasoning you're going to use, or that's how you would connect that with your prediction up here.